measurement of turbulence at LAPD.
Hi, thank you. Most of you don't know me. My name is David Schaffner. I'm working for Troy Carter at UCLA and looking at turbulence and flows on LAPD. And full disclosure, I am an experimentalist, so take that in consideration when you're asking questions. Take it easy on me, yeah, sure. I'm also just a fourth-year grad, so. Anyway, so I'm going to talk about the spontaneous flows that we see in LAPD and look at how they scale with the field, and also the connection to those flows with turbulence and transport. And we'll go through a technique of biasing that we use to actually control the flows and create our own driven flows rather than relying on the spontaneous flows in LAPD. So these are fairly broad topics. So I have a lot to cover. Just a review, for those of you who don't know, LAPD, the large plasma device, is, as it says, large, 17 meters long, 1 meter in diameter, creates about a 60 centimeter plasma. The magnetic field ranges at about 1 kilogauss, densities 10 to the 12th, and we run at a rate of 1 hertz. So these are very statistical measurements that we're taking here. So turbulence and transport in LAPD. So LAPD is very suited for turbulence studies because of its large size, specifically the ion radius to plasma size perpendicular to the B field is on the order of 1/100th to 1/300th. And this ratio allows a number of unstable modes to be supported, and so edge turbulence is broadband and fully developed. In addition, the large size allows the perpendicular transport to compete with parallel losses. And so you have a density gradient that's fairly gradual to be allowed to be set up, which I'll be showing in a second, compared to smaller machines. And the turbulence is electromagnetic, and the beta that LAPD works at allows drift Alfvén wave coupling and turbulence to be observed. And also the setup, as I suggested with biasing, allows us to bias sections of the chamber in order to drive flows using the biasing in addition to the spontaneous flow that we see in LAPD. So these are some typical profiles. You can see the density is fairly gradual from the center of the machine to the radius at about 50 centimeters. And the density gradient begins about 10 centimeters before the edge of the cathode, which not indicating in that plot, which is at about 28 centimeters. The temperature falls off a little bit steeper. It's fairly constant in the cathode edge region and only begins to fall off just at basically the cathode edge, and then is fairly flat after that. And similarly, the plasma potential is constant in the cathode, within the cathode region. And then when you get right outside the cathode edge, you see a little bit of an increase in potential, which indicates E cross B flow right at the cathode edge. And then the potential reverses value and decreases basically linearly to the wall of the chamber, which is at ground, so zero potential. And so both changes in potential are indicative of E cross B flow in those regions.
Are those profiles taken during the active sourcing phase? Or?
Generally what we do is we will, the plasma discharges, and we'll begin looking either just towards the very end of that initial discharge when the primary electrons are still streaming through, or often we'll wait until the discharge decreases. And there's a brief moment where the density tends to remain high just after the discharge turns off. The temperature will drop, so kind of in that region. So we do try to avoid primary electrons, but I would say for the most part these are taken just as the discharge is turning off in LAPD.
What axial position are you taking?
I'm sorry?
What axial position are
Along these are, this profile is somewhere in the middle. The axial variation doesn't change too much. I don't have anything to show what the change. It's fairly uniform axially. So we tend to look generally in the middle of the 17 meters or so of the plasma. But yeah, so it's fairly. I mean, there's potentially some variation axially. We don't like to think about it, but it's not too bad. Okay, so why are we looking at flows? Well, flows are critical to stability and transport, has been shown. Edge rotation has been linked to H mode transport, has been linked to H mode in transport suppression in tokamaks. And LAPD exhibits a plasma with broadband turbulence and spontaneous flows. So we are interested in what is the role of the turbulence in these flows and how do these flows correlate with transport. And also we're interested in the role of the boundary conditions and boundary processes to the flow in LAPD. Just like in a tokamak scrape-off layer, the flow is determined by transport to the diverter, magnetic geometry, et cetera. So we want to understand how boundary affects flow in LAPD as well. So here's a snapshot of the spontaneous flows that I keep mentioning. So on the right side is our typical density gradient, core density. Here, density decreases basically around the cathode edge and then is fairly flat near the edge. And as you saw with the potential profiles, that there are some electric fields specifically in the region of the cathode edge. And so we see what I'll refer to as a shear layer flow in the cathode edge region, which is in the electron diamagnetic direction of LAPD. And then there's a reversal of flow just beyond the cathode edge, and as you approach the edge of the chamber in the ion diamagnetic direction. So all of these flows were measured using a 6-sided Mach probe.
These are azimuthal flows, right?
These are azimuthal flows, yes. So the flows are measured using a 6-sided Mach probe, which measures both parallel and perpendicular flow, and then we can extract the perpendicular flow from that. And I do make an assumption that these profiles are zeroed out in the core. We assume that the flow is zero in the core, seems likely given the potential profile, but there are some asymmetries in the probe which kind of will cause that to deviate. So this has been zeroed out in the core region, and so we assume the flows take the directions they do. So you can see there's strong shearing in the density gradient region. So how do these flows scale with magnetic field? Well, it depends on where you're looking. If we're looking in this shear flow region, we see that the flow actually scales with the field. Stronger field, stronger flow. But then when we look towards the edge, for the most part, the scaling is inverse with field. Now this seems reasonable if you argue that that's E cross B flow. As the B field increases, you would expect the flow to decrease. But the scaling for the shear layer flow is not understood and is under investigation. And the fact that there are two different scaling laws suggests that maybe there are multiple mechanisms for these flows. Did you have a question? Okay. Just comparing the shear flow to the density and density gradient, we see, as I showed before, that the shear layer flows are scaling with the field, but there aren't any clear indications that the density or the density gradient scales with the field. So if a possible drive for flow is density and gradient driven instabilities, it's not obvious from the density gradient if there's any cause for why the flows scale with field like they do. So perhaps there's an alternative mechanism in addition that causes the field differentiation. So as I stated, the origin of the spontaneous flows are not clear. The edge flows appear to be driven by penetration of the electric field from the chamber. as evidenced by the inverse field scaling. As I mentioned, E cross B flow, it is reasonable to think that it would scale inversely with the magnetic field. And later I'll show a technique we use in edge biasing, which also supports this idea that it's electric field penetrating the chamber, creating these flows on the edge. But the shear layer flow is still not well understood. It seems to be driven by a different mechanism. Some of the things we've looked at, and I'll look about a little bit at turbulence in a second here. We're also going to be looking at the role of Reynolds stress in this flow. And it could also be a boundary effect, which is also in the preliminary stages of investigation. So here's a kind of a very wide survey of possible boundary conditions that we've changed. So let me try to clarify what's going on here. So our usual configuration in LAPD is the chamber, cylindrical chamber, and a fairly constant magnetic field. Certainly in the middle region, maybe it deviates a little bit towards the end. We have an anode and a cathode on one end, which are separated by about 1 meter. And then on the far end, we have a metal end mesh, which is electrically floating at the very end of the chamber. So this is the standard configuration that we use for most of the data that's taken here. And so we're at least initially going to concentrate on, in terms of boundary changes, looking at the end changes and see what we can affect there. So the ones that I'm showing here, this end mesh we could actually just rotate out of the plasma. So instead of the end mesh being at the end, it just kind of flows to the end of the chamber, the end of the cylinder. We can also ground the chamber, and then we could also modify the fields, including flaring the field at the end. So we decrease the magnetic field at the end so that the field lines then are colliding with the wall instead of going to the end of the chamber or out of the chamber. A magnetic mirror configuration and a small cathode field configuration, where in these two cases we differ the field that's surrounding the cathode. So just looking at the effect on the flow, there's not too much variation. There's certainly very little variation in the shear layer for the affecting the end mesh. The only thing that does seem to affect it a little bit is the grounding the end mesh to the chamber, which tends to increase the flow overall. And then there are these structures that we have seen that we don't really understand yet, so need to look into that further. Maybe there is an effect there, maybe that's just the probe not working correctly, we don't know. It appears that flaring the field and just rotating the end mesh out seem to produce the same effect, which is to actually decrease the flow in the edge region here compared to our typical arrangement. And so they seem to basically create the same effect. But there's nothing very, very strong in terms of modifying those particular boundary conditions. Now, modifying the field, specifically modifying the field around the cathode edge, does tend to change the profile of these flows, but more in the sense that it just tends to map the plasma onto different size scales. So increasing the field in the cathode and then broadening it tends to kind of map the profile onto a larger area, and so that's what we're seeing here. Whereas decreasing the field in the cathode region tends to shrink it. So again, in terms of the shear layer flow that we're seeing, the peak in the center, there doesn't appear to be very much variation. The positions of where the shear layer occurs change, but the shape and amplitude don't appear to change much. There does clearly have some effect on the edge flows, but it's hard to say whether that's just because the size of the plasma has changed, which is potentially an important effect. But in terms of the spontaneous flow at the shear layer, there doesn't seem to be very much effect by changing at least the end boundary conditions.
Can I ask you one question?
Yeah.
You asked earlier. How big is E phi over T in the equilibrium effect? Suppose I went to the center.
E5 over T. So let's see, the plasma potential sits at about 40, 45 volts, and temperatures on the order of 6. So maybe about 10 times. Am I answering that correctly? Your plasma potential versus temperature, correct? Yeah.
That's bigger than Troy's.
But what's the potential at the cathode? Sorry, the anode.
The potential at the anode is, well, there's the anode cathode potential, which tends to set the plasma potential, is the maximum value is about 60, 70 volts. But we found that the plasma potential actually tends to drop a little bit from that, or at least I found that the plasma potential tends to drop a little from that. So I'm not sure what number Troy is referring to. He's saying
Troy
it's
tells us that it's usually a little higher, plasma potential is a little higher than the anode, potential.
okay. I'll have to maybe that's I don't know if we've gotten Troy to call in yet or not, but
and this is an unbiased case. So you're not biasing.
yeah, this is all unbiased. Yeah, I'll have to double check that with Troy.
So we're interested in this question because sheath effects would lead you to think that E phi over T is going to be on the order of about 3 or so.
That sounds like Troy.
Anyway, just wanted to
Okay.
pick your brain about that. You need to direct
All right. Well, we'll address that. That is an important point. Okay. Well, let me, assuming. Okay.
It's an answer to a question.
I think it is actually. What's the name of the person?
Troy Carter.
Is that Troy?
You're kidding.
Yes, it is Troy.
Yeah.
Oh, they put this thing online, this whole business?
Troy,
Yeah.
you're better than Google. We ask a question and the phone rings.
Don't forget, that's going to be 30 seconds behind him. So there's going to be a big lag.
Uh-huh.
Can you guys hear me?
Yes.
Yes.
We can hear you. Can you hear us? I think there's a time lag.
Yeah.
Yeah.
Okay, all right. Yeah, I think Barrett was saying that the anode potential, the plasma potential is a little above 10. That's what we tend to see. The anode is about 50 volts or so, a little bit below that.
Yeah.
The plasma potential is maybe a few volts above that, something like that. The cathode tends to sit near ground, near chamber wall potential. Yeah.
Okay.
Excellent.
All right. Shall I go ahead and just go on? Okay.
We're moving on, Troy.
Okay, so I want to switch gears to look at the turbulence that we observe in LAPD. And as I mentioned, turbulence tends to be broadband, especially in the regime in which drift wave modes would be active, which is 10 kilohertz or so. And also, I'll briefly talk about some of the intermittent turbulence that we see in LAPD and the edge core. Not nearly as much on this as in the density gradient regions, but I will talk about it a little bit and how that relates to flow and turbulence and transport. So, looking at the spectra, there does appear to be a connection between the flows and suppression of turbulence. So if we look at this comparison of spectra for 4 different magnetic fields and kind of aligned with the flow profiles for each case, the first thing you see is that there is significant Doppler shifting, especially in the 400 Gauss case, due to the high flow region. So you see that the 400 Gauss case has the highest flow, and the most Doppler shifted frequencies. You do see that to an extent in other fields, but not nearly as evident in the 400 Gauss case. What's also good to point out is that in the shear flow region, the shear layer region, especially along the edges of the shear flow peak, you tend to see a drop in spectral power. So if we look at where this peak lies in the spectrum, you see kind of right after the peak where the shear layer, the shearing rate is highest, you do see a drop in fluctuation power in all three cases. You see one here and see one there. And then you also see, interestingly enough, a decrease in power that kind of correlates with this inflection point in the flow. So as you get towards the edge, which is about 40 centimeters, 40 centimeters is about where the density gradient starts to level off. And so you see a change in flow shearing rate here, and you also can correlate that to a decrease in fluctuation power. So that's something that we are also going to be looking at in the future. Don't really understand what's going on there. So in general, there is some evidence that turbulence is reduced with higher flow shear, especially in the cathode edge region. But it's not always observed, as you can see in other places where you would suggest that there's strong shear. You actually see an increase in fluctuation frequency and power. So is that a real effect, or maybe this is just a competition between Doppler shifting and the reduction of turbulence that we're seeing? So it could just be a measurement effect. One of the things that we are going to also do in the future is recast these plots in K rather than frequency, which should kind of cancel out the effect of the velocity. So we can look at the spectrum without the effect of the flow. Yes?
So I notice as the field gets higher, there's like no turbulence at the very outside. Is that because there's no plasma there?
Not really sure. The densities don't. I don't unfortunately have a plot that shows the density profiles with respect to field, but they're not very different.
Okay.
The density doesn't change too much in terms of field. So
It's interesting at the very highest case. I mean, there's very little flow shear there.
yeah.
Yet there's no turbulence in the outside.
Yeah.
5 to 8 centimeters. So.
Yeah, so that's definitely under investigation. So another way to look at it is just summing those spectra plots versus either summing over the frequencies for each, summing over the each radius for each frequency, and you can see here that the spectra for each field doesn't vary too much. So there is some. I mean, if you actually kind of spread this apart, there is some scaling in field in terms of a higher field tends to decrease the turbulence in most frequency at most frequencies in this regime. Looking at the power summed in frequency per radius is also a little more illuminating, and you can see that there's a clear variation in field, especially in the cathode edge region, where 400 Gauss has the largest fluctuations, and it decreases from there. And 400 Gauss, in fact, has almost twice as much as the next few fields, whereas the variation doesn't change as much as you increase the field as you get higher in field. Now, that drop in fluctuation power that I noted at about 30 centimeters, you can see here as well, and each field has a slight drop in power, which matches the point where the absolute shear flow is at a maximum. And also note that beyond 40 centimeters, that the fluctuations still scale with field. So kind of as you pointed out, there basically are no fluctuation, very little turbulent fluctuations at 1800 Gauss, despite the fact that the flow shear is greatest for the 400 Gauss case. So again, is this a measurement problem? Is this just our measurements of the frequency being Doppler shifted and kind of overshadowing what or any type of suppression that we're seeing, or is this a real effect? So that's something that we want to investigate further as well. Now, actually, something that came up just in this week, looking at separating the spectra depending on whether we're looking inside or outside the cathode edge. So basically, summing up the frequencies in the region less than 28 centimeters for inside the cathode edge and greater than 28 centimeters for outside. And there's a clear distinction in both the spectrum and the crossphase between density and potential. So with inside the cathode edge, we tend to see crossphase between density and potential at about 1, since they're in phase that is drift wave-like. But when you get outside the cathode edge, you tend to see the density and potential out of phase, which isn't drift wave-like. So, what we could potentially be seeing is just two different modes operating at two different positions, one potentially being drift wave mode, outside perhaps flow-driven or even sheath-driven modes on the outside. And this also potentially is the explanation for this dip in turbulent power. It may not actually be turbulent suppression, but just we're seeing two different modes operating, and kind of we're seeing that transition. So that's something that we're trying to, and this just came up just this week, so we don't really have much more insight in that than these plots show.
Just a comment.
Yeah.
So have you tried to go beyond frequency spectra to estimate which of the modes are really driving more transport? I mean, high frequency shortwave modes might be in there, but not doing much in the way of cross-flow transport that you thought about.
No, I mean, those are things that are definitely on the table for looking at it. At least in my work, the work in looking at frequency and turbulence is fairly new. So I'm just starting to investigate a lot of those things. So definitely, if you have some suggestions on what to do, I'm happy to hear them.
And when you do that, are you going to actually do the proper phase correlation to actually calculate that transport?
Sure. Yeah, I would assume. Well, yes.
But you guys have the capability of doing that.
I would have to double check, but I'm not sure at the moment. But I would assume we do. Yeah.
Can you measure K parameter?
That was actually a discussion that Troy and I were having yesterday, and we're not sure. The problem being that the K parallel in LAPD tends to look more like a standing wave than a propagating wave. So the techniques that we have to measure them aren't well suited for measuring K parallel. So that's something that we have to think about, and are certainly open to suggestions on how we could measure K parallel. But that would definitely illuminate what modes we're looking at. So yeah, so that definitely came up, but it's not clear that we can. It certainly would like to. Perhaps one way we can try to do it is related to these 2D correlation plots, which we use to measure the K-perp spectrum. Now, these correlation functions are made using two Langmuir probes separated about 1 meter apart or more axially in the plasma, and consists of one reference tip that's basically in one spot, and another Langmuir probe that's swept in an area about 20 by 12 centimeter plane, and as you can see, that plane sits about surrounding the cathode edge where the peak flow is. So we can kind of look before and after the shear flow layer. And the most evident effect is, as we go from kind of inside the cathode edge to outside, is just the effect of the shear layer on the turbulent structures. There's a definite spreading in azimuthal correlation length, and you could almost see that the shape matches the flow profile as we look at different points in the plasma. And the fact that the correlation length isn't reduced as some may think would happen in high shear regions, where rather the shape of the structure is just more spread out rather than cut off. Now we can, as I mentioned, we can extract, kind of back of the envelope calculation, extract a K number for these fluctuations, and then convert that into an M number based on the radius. Just using the fact that a very rough estimate that the wavelength of the fluctuations are going to be on the order of the azimuthal correlation length. So just kind of using that estimate, we get an M number around 30 or 40 for these correlation lengths, which is consistent with predicted fastest growing drift waves as done by eigenmode solvers using the Brudzinski fluid equations.
What does that correspond to K theta rho r?
K theta, what values?
Yeah.
Well, let's see. K theta is. I have to do the calculation in my head because I don't.
Is it like 1
Well, let's see.
or
The rho I. Okay. Half.
half is that's
Okay.
K
I'm sorry.
K theta rho s.
Yes. It's about a half. Okay.
Rho
Rho I or rho S?
Rho I is smaller than rho.
Yeah.
Gi
In-
is steeper rho s.
Yeah. Actually, in the next plot, I have some connection to sound rate gyro radii and ion rate gyro radii. So let me just briefly show in field we also get a scaling and correlation, scaling in the correlation size, an inverse scaling with the correlation size. And here we have the this is the radial correlation length in reference to the gyro radii. So the sound gyro radii tends to be on the order of about half a centimeter. Ion gyro radius about half that, about 0.25 centimeters. So as you can see, at least the radial correlation lengths tend to be about 4 to 5 for the sound, 4 to 6 for sound gyro radii, 8 to 10 for ion, and so it's about that value in azimuthal correlation length as well. Okay, let me just briefly cover some of the intermittent turbulence that's seen in LAPD. Intermittent turbulence is patchy in space and bursty in time, and its signature is a non-Gaussian amplitude distribution function, amplitude probability distribution function. So you definitely have skewing towards these high density fluctuations, and these are seen in edge magnetic confinement devices and explained by the presence and propagation of structures, seen nearly in all such devices. The propagation of structures are tied to polarization by drift changing, and transport by intermagnetic convection is very important in the edge of confinement devices and may be linked to the density limit. So this is a sample of intermittency that's seen in LAPD. So you can see this. This is a time profile of fluctuations on the edge, the far edge of the plasma, and you can see these bursty intermittent signals. We could also do cross-correlation averaging, cross-conditional averaging to try to image these density fluctuations. So the question is how does this intermittent turbulence affect plasma flows, or vice versa? Is one causing the other, one affecting the other? So that's something that we're also in the progress of trying to understand. we can look at how this is a contour map of the probability distribution functions as a function of radius. And so you can see if we overlay that with a typical flow profile, that in regions of high flow, you do get increased intermittency. So the skewness tends to increase in high flow regions, and regardless of whether the flow is, regardless of the direction of the flow. And so you also tend to see that it peaks, the level of intermittency peaks in regions of high flow. So in the shear layer, we have peaked intermittency. It tends to decrease a little bit, even with the shearing, tends to decrease as the flow decreases, and as the flow starts to increase in the other direction, we do see increased intermittency as well. So it appears to be associated with flow regardless of what direction it's going in. Okay, now I want to switch gears a little bit and talk about biasing, which is, we're just applying a voltage, a strong voltage on the chamber, which is can be set to flow. Yeah, sorry.
Sorry, before you
Yeah.
switch gears too much.
Yeah.
Do you guys do these plots of kurtosis versus skewness, like the Torpex?
Yes, we can. In fact, I had a plot in here, but I took it out. But yes, we can do that and look at.
Does it look like the canonical parabola that people talk about?
Well, when we did something like that, it wasn't clear what we had. So I think it's something that we need to do and look at in the future for sure. Okay, sorry. Shall I go ahead and move on to biasing? Okay. So let me biasing. Yes. So basically, what we're doing is we're applying electric fields to. If we positively bias, we're imposing strong electric fields pointing radially inward. If we negatively bias, ideally we're creating electric fields that point radially outward. And so this is a way of, rather than relying on the spontaneous flows that we see, of actually creating our own flows that we can somewhat control. And the way this works is that we actually have each chamber in LAPD can be electrically separated from one another. And so we take the middle two chambers and float them from ground, and then apply the bias voltage to that entire chamber between negative 100 to 200 volts. And it's important to note that the regions around the cathode in the end remain grounded. So it's just the center section that's being biased, and it's also just and the bias occurs for about a quarter of the period of the discharge. So if a discharge is on the order of 12 milliseconds, we bias for 4 or 5 milliseconds in the middle of that discharge.
Why not longer?
I'm actually not sure. I was not the one who decided how to set up the biasing, so I don't know if there are issues with biasing for the entire time, or it could just be just the circuit that's the best they can do. I don't really know, but as far as I know, it's just kind of biased in.
Wanted to see transients.
Did you? I guess Troy is saying to look at transients of the change, so you don't want to bias the entire time. And an important
Time before and after to see how things develop, basically, in the plateau.
Okay. And an important observation that we see with the biasing is, and I'll get to, is we do see a confinement transition, an H mode in LAPD. So what does biasing do to the potential and flow? Well, it's a very clear effect. With the background, we saw that the potential tended to head towards zero as it approached the wall. When we positively bias, the potential just ramps up. It doesn't get to the voltage that we set it at, but it does increase fairly linearly towards that. And also notice that the biasing, the influence of the electric field doesn't really affect the cathode edge region. The only thing that it does do is tend to drop the plasma potential a little bit. Why it does that, not really sure. So really the only effect of the flows that we can see from biasing are again beyond the cathode edge region. So we just really cannot affect what's going on in the cathode edge, within the cathode. And then you can see here, as you would expect, the flows reverse. So biasing positively tends to drive all the flows in the electron diamagnetic direction. And also fairly strong flows on the order of the edge flow, the same, about the same magnitude as the edge flows we were seeing in the background, just in the opposite direction. And the scales also flow, the flows also scale with biasing. So we can, this is good in that we can somewhat control the shearing rate that we achieve with the flow and try to determine so we can try to focus on what kind of shearing rate that we want to look at. And again, you can see that the potential is affected by the flow, and you can see that the shear layer flow that we saw in the spontaneous shear layer flow that we saw in the unbiased case tends to get washed out by the biased flow, whether that's because whatever's going on, just you don't see it anymore, or just it's being masked by the amount of flow that's going in the electron diamagnetic direction is unclear. Now we also tried biasing negatively, so a negative voltage on the walls would tend to collect ions predominantly, but as what we're seeing is that that's limited by the ion collection. So the LAPD becomes a giant Langmuir probe, and so it hits ISAT levels and can't really draw any more ion current, and so biasing negatively basically doesn't have any effect. It's really just, at least for most of the gradient region, it's just the same as the background case. You do get a little bit more flow on the edge, but other than that, really positively biasing is the only thing that we can do to really control the shearing that we have. So one of the important results of doing this biasing is that you do see the presence of an H mode in LAPD, and you can see the gradient tends to steepen around the cathode edge from the biased to the unbiased case, and that the temperature also doesn't decrease. It tends to stay, it drops a little bit, but then tends to stay high in the edge region rather than dropping to low values like in the unbiased case. And there appears to be a bias transition, a threshold for the bias transition based on how much radial flow is penetrating. So at some point, the transition occurs at a certain bias due to a given amount of flow, and then basically doesn't increase anymore. And that this threshold increases with B, which is much more clear in this plot, which is 4 different fields, and we can see that in low field case, when you get into about 100 volts and you start seeing larger amounts of flow, you get this confinement transition from, this is the gradient of the density, goes from fairly small to fairly large. So there's a stark transition to the confinement transition, and that effect starts to dissipate in that area, or it begins to increase in, the transition point begins to increase at 800 Gauss, and then we don't even see the transition at higher field. So whether that means that you just need to drive more voltage in order to see it, if we were to double this voltage, would we potentially see at some point see the confinement transition, or if for whatever reason the field eventually just eliminates the ability for the plasma to transition, we don't know. So we can compare now a similar plot as before to the flow to the spectrum, and as we saw before, when you have larger amounts of flow, you do tend to see Doppler shifting in regions of higher flow. And you do see some reduction in the turbulence, although not very much, at least certainly not in amplitude. The turbulence is reduced, but not by that large of an amount. And also the fluctuations tend to steepen on the flow gradient, the shear gradient. We also do correlation plots, and just like in what we saw with the spontaneous flow, the shear flow from biasing just tends to stretch out these structures, the correlation function plots, rather than reducing the radial decorrelation. And also, just again looking at intermittency, we do see that the increase in bias tends to widen it tends to increase the skewness of these plots. So you do see more intermittency with biasing, which based on the conclusions of the earlier plot with the high flow region, we get a lot of flow with biasing, so naturally we get a increased intermittency. But it's interesting because even with the increased intermittency, we do see the confinement transition. So there's somehow some competing effects here, that we see more intermittency, which is associated with particle transport in LAPD, but we also see this confinement transition. And so here's a comparison of the two plots here. It appears that the intermittency is more related to the flow itself than to the shearing rate. Okay, so in summary, I showed that the parameters of LAPD provide a fertile environment for the study of turbulence, transport, and flow, predominantly due to its large size, but also some other aspects of it. And that we do see spontaneous flows in LAPD, and that those flows vary with field at the cathode edge, but inversely with the field at the cathode edge, but with field in the chamber edge, and that the origin of these spontaneous flows is still under investigation. Our turbulence that we see is in the driftwave mode regime of frequencies and is broadband and generally scales inversely with the field. The sheared flow appears to suppress some turbulent fluctuations, but not all. So there definitely needs to be more investigation into what the actual effect of the shear flow is.
I'll make one comment on that.
Yeah.
You shouldn't be too discouraged, because in the case where you're increasing the shear flow, you're also seeing a steepening of the gradients. Is that true?
Yes, that is true.
So you're increasing the drive of the modes, but you're actually seeing somewhat of a reduction.
Mm-hmm. Mm-hmm. Yeah, that's absolutely true. So we're trying to understand things that are competing against each other, and so trying to figure out what does what is definitely on the table. Okay, and again, we did affect some of the end boundary conditions, and they don't appear to have too much an effect on the shear layer flows. There is some effect on the edge flows. That's also on the table for more investigation, as well as the intermittent turbulence seen in the edge region. Does seem to have some connection to the magnitude of the flow, and of course that we can use biasing as a tool to try to directly control what flows that we have in LAPD to try to extract more scaling relationships. And so the important slide, future work, what do we want to do next? Well, we want to look at the spontaneous flows and bias-driven flows in terms of Reynolds stress. So that's actually some data that we've taken in a recent run that needs to be analyzed and see if there's any connection to the Reynolds stress, as well as to particle flux and these density potential cross-phase measurements. We also want to look at the K spectra rather than the frequency spectrum for the correlation functions to extract out try to better extract out some of the modes, potentially looking at K-parallel if it's conceivably possible. Also looking at how intermittency affects turbulence flow, transport, and momentum transfer. One of the ideas in terms of boundary effect was to potentially create iris-like limiters in LAPD to try to get a better handle on what the end boundary conditions are in LAPD and see how we can affect them. And of course, continue comparing our results to simulations such as BOUT, which is something that a code that Troy works with Popovich and his other grad student Brett Friedman on, and then potentially gyrokinetic code if it's found that LAPD is in a regime where that would have maybe the Brzezinski fluid equations aren't enough to explain what's going on in LAPD. And
Simplify that on that, or elaborate on that?
Sure.
In what way?
I'm sorry?
In what way are you thinking that the Brzezinski model is insufficient?
Well, specifically, if you look at the plot of here, where if our structures are related to the sound gyro radius, so the size of what's going on isn't that much larger than what's going on at the ion gyro radius, where presumably kinetic effects would start to come in. So I mean, it's not. I'm not trying to convince you that it's not enough. It just, there is potentially some evidence that the fluid equations may not be enough. But
It's K per rho I or something. TI is like 1/5 TE or something?
TI is, well, in these calculations, TI is on the order of about 1 EV. In LAPD, it's not well measured, but what has been measured puts it on the order of half, maybe 1/10 of an EV to an EV TI. So TE in the core tends to be between 5 and 6 EV, and then decreases down to about 2 EV. So in the core, it's maybe a factor to 10 to 20. Towards the edge, it's a potentially smaller factor. Although that is something that hasn't, at least I don't have any measurements on of what the temperature profile, the ion temperature profile looks like, which would be interesting, but that's extremely difficult to measure.
But if you're K rho S and a half, and then you've got a full decade to go down on which are K per rho I, how would that be a super small effect?
That could be true, yeah.
So there might be other issues with the fluid enclosures.
Okay.
If you try to think of your turbulence extremely primitively in terms of the Hasegawa-Wakatani.
I'm sorry?
The Hasegawa-Wakatani model,
Okay.
the collisional drift waves,
Okay.
contains a single parameter that people call the idioticity parameter. I was just wondering if you happen to know where that stands for your...
No, I'm sorry, I haven't even heard of the model. As I said, I'm an experimenter. I haven't encountered that. But what was the name of the parameter again?
Well, the idioticity parameter.
Idioticity, okay.
How does E5 compare to E5 wiggle compare to T wiggle?
Well, it's a collisionality parameter.
Uh-huh.
Basically.
Okay.
On the one extreme, you get essentially a strong two-dimensional turbulence type limit. In the other extreme, you're close to, the Hasegawa-Mima. Electrons are almost adiabatic.
Uh-huh. Okay.
Right. I was just trying to get a sense of the collisionality.
That I don't know. I'm sorry, I can't answer that.
You had a plot with this interesting channel, and I must have zoned out. Could you explain what that is?
I'm sorry, which?
There was a slide where you had this channel. Yeah, this one.
Yeah.
What is this picture?
So this is a series of these probability distribution functions. So these probability distribution functions. So the probability of a given ISAT value normalized to the RMS value fluctuation. So I create one of these for each radial position and have just overlaid them as a contour map. So when you're seeing a higher skewness in the positive the positive normalized amplitude value. That's the kind of the skewness of
So
the.
you're just plotting the PDF versus
Exactly.
the radius.
Exactly, yeah.
Okay.
Just so you can see, how these changes, how the skewness relates to areas of higher flow. Yeah.
And the radial correlation, when you compare it to the azimuthal correlation, you have a plot of that.
Let's see.
That's a look.
These plots here.
X is your radius,
Yeah, these are the radius.
and azimuthal. Okay, I see. Yeah, the reason I was wondering is there was some ideas back when about, you don't have any magnetic shear, right? You're just straight field.
Yeah, it's just straight
There
field.
were some ideas that you would get a spontaneous formation of a flow channel, a radial flow channel. And,
With magnetic shear.
no, without magnetic shear.
Ah, okay.
But you don't see any evidence for that at this moment.
What would you see?
In other words, you would see a longer correlation, you'd see a burst of flow with a longer correlation in radius than you do in azimuthal. Or,
No, not that I'm aware of, but that's something that we can try to look at closer. Yeah.
Today's talk is mostly aerostatic.
Yes, well, the measurements that we're looking at are fluctuations in density. Well, a drift wave is in LAPD it could be. I don't know if it's necessarily clear that it is. It's an area that I'm still not as familiar with, so I'm not sure I can adequately answer.
Today's talk is almost aerostatic, but I guess we're not done the astrophysical simulation for the outcome rate.
Yeah, that'd be good.
So I
We're
think
talking about authentic turbulence.
what was the data?
Beta tends to be about a 10,000th.
So I just thought if there is a different regime where this operating on where simulation.
Potentially, yes. Maybe I'm not clear on what the difference is. So.
For these little betas, we would think it was all prescribed. But you can reach higher data, can't you? Using what you said.
I'm actually not really sure.